Orbital velocity. Purpose. I will understand a satellite's motion. In particular, we're looking at the velocity and the time of a satellite as it goes around a planet. Relevance. Satellites are a crucial part of society today. We should know the basic science involved in placing them in orbit. Success. I will be able to explain why a satellite stays in orbit. I will be able to calculate a satellite's speed. Tonight you have some homework to do, and we have a quiz in a couple periods, a couple lessons. Please make sure that you are asking the teacher for any questions on your homework. Number 1, draw the path of a slow cannonball being shot horizontally off a 50-meter tower to a flat plane. Then draw paths for a very slow cannonball, a very, very fast cannonball, and a medium one. So for a cannon way up here, if they shot a slow cannonball, it would just go kerplop like that. A very, very fast cannonball would go along that lines. And a medium one would look like that. Number 2. Draw the path of the same cannonball being shot off the same tower, but over a hill. Before we were on flat ground, now on a hill. Draw a very slow ball, a very, very fast ball, and one with a just right medium speed. Draw people on the hill and how high they would say the cannonball is above the ground if the ball had that special velocity. So again, here's the cannon. A very slow cannonball would just go kerplop like that. A very, very fast cannonball would go like that. But one that was just right would go like that. So a person standing right here at the bottom of the tower, they would look up and they would say that the cannonball was 50 meters up. A person over here would look up and they would say that it is also still 50 meters up. Person down the hill a ways would look up. The cannonball has come down a bit from the original position, but the person is also lower. They would say that the cannonball is still 50 meters above the ground. And same thing over here. That is still 50. So the cannonball is falling downwards, but the ground is also curving at the same rate. And so the cannonball is still staying 50 meters above, no matter where it is along this path. The same kind of a thing happens with putting satellites into orbit. Imagine a very tall tower and a cannonball with just the right velocity for orbit. So here's the tall tower at the North Pole. And as we shoot the cannonball, it's going to curve downwards, but the Earth's sphere is also curving downwards. And so it's going to stay at the same elevation. As I turn the cannon here, it's going to continue going and trying to fall down, but the Earth is also curving, and the cannonball misses the Earth. And that's just going to keep on going all the way around. It is continually falling towards the center of the Earth, but the Earth's curved surface follows the same path. And so the cannonball is always the same height. And we call that in orbit. When a projectile is fast enough, it falls downward at the same rate that the Earth's surface curves as a sphere. The cannonball then remains the same height above the ground. It keeps on going forever, and we call that in orbit. Number 5, the velocity that gives a projectile the right path is called orbital velocity. It depends on how big of an orbit the object has. The equation for orbital velocity is this right here. V is the orbital velocity. That's going to be in meters per second. The capital M is the mass of the central body, whatever it's orbiting around. It might be, well, usually it's the Earth, but we have sent space probes around all the planets, and they're orbiting those. Not very many of them, but we do have a few, and there are some that are going around the moon. It's going to have units of kilograms. The R is the distance between centers, between the core of the Earth and the core of the satellite, or whichever bodies we're talking about, and that has to be in units of meters. And G is the gravitational constant, which is that funny number right there. If an object tries to orbit, but it has a slower speed, then it won't arc as far as it needs. It'll be like this slow cannonball. And the arc will be too steep, and it will land on the surface. It'll fall on the surface. Whichever phrase you like. Number 7, if the object moves too fast, then its path won't arc at the same rate as the planet. Its path will be too straight, not arcing enough. That's going to be like this really super fast cannonball, which goes off farther and farther away from this sloping hill. So this will lead the object to fly into outer space. Into the solar system, far, far away, never to come back. So with your homework problems, you might have different kinds of situations where we have space probes, satellites going to different parts of the solar system. So you will need to be able to go to the web and search out their radius and mass. I will let you do that on your own. It's not terribly important that we do it right now. You can do it as you need it in the homework assignments. Okay, so now we're going to have some story problems, and I'm going to pause the video here, or stop it here, and load this up, and then I will have a second video, part 2, that will go through these story problems.